Jason is spending the week fishing in the Springville fish hatchery. Each day he catches 3 fish. For each hour he spends fishing, the relationship can be modeled by the equation y equals 3x, where x equals the number of hours spent fishing, and y is the number of fish caught. Hopefully that does make sense, because x is independent, and y is dependent on the independent variable, meaning the number of fish caught will have to depend on how many hours have been fished. So, we need to complete the graph and the table below, but let's do the table first. First off, they've told us some number of hours fishing, and so it looks like the first time you went fishing for 3 hours, and up here, according to the equation, y equals 3x. Y is the number of fish, x is the number of hours, so 3 times 3. If he goes fishing for 3 hours, he should catch 9 fishes.
And there's no y-intercept.
Well, as it turns out, if he went fishing for 2 hours, how many fish would we expect him to catch? 6.
3.
What if he went fishing for 1 hour? Because that's how many went the next time. 1.
6.
Sorry, 3. 2 hours again, he should catch 6 fish.
0.
So if he doesn't go fishing at all, naturally, hopefully he should catch
He should
0
get
fish.
around 37 fish.
Well, what if he goes fishing for 4 hours?
12.
12 fishes caught, okay? All right, now that we have these, and these are all ordered pairs for us. So the first ordered pair would be this 3 9er. Then we got 2 6 and 1 3 and all these other ones. So before we graph these, we need to label the axes. And it already told us that x is the number of hours fishing. Hours. And then the y is the number of fish caught. Fishes. Well, then we just need a scale to match these. And the number of hours fishing only goes up to 4. So we can go, there's 1 hour, 2 hours. But I'm going up 1 hour every 3 lines. And 5 hours. Now, it didn't go up to 5 hours, but that's okay. We can have some empty space. But the least empty space possible it's more better. So, the number of fish caught goes up to number 12. So, we'll go up by, looks like we're going to have to go up by ones each. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That'll be an important one, and it goes all the way up to 15. Very good. All right, now that we have the labels for each axis and the scale, all we need to do is graph these points. So, we'll start with 3 9er. 3 9er. Bam. Then we got 2 6. Bam. 1 3. Nailed it. 2 6. There it is again. 0 0. And then 4 12. Right in the fish. 10, 11, 12. There we go.
And then the next one is the fishing count.
There it is. I think I went over too far. Yeah, it should be right there. That's better. All right. So we've graphed all these points. The next question is, do we connect the points?
No. Yes.
No.
Yes.
No.
We
Why?
should.
I don't know.
Dang.
You should, because then you could see it better.
Interesting.
No, because it's not like. Because.
It's you,
It isn't
right?
a steady rate. Well, it is, but it's.
You're on the right track, yes.
So the answer is free. Don't, because you don't know when it's going to stop.
No. So let's go back to, it's not a steady rate, right? More specifically, well, it is kind of a constant rate of change. It's more that you can't really catch half a fish, okay? So you either catch a fish or you don't, meaning we wouldn't connect these points. That is what we call a discrete graph. We've talked a little bit about those before, but it has been a little while.
Okay.
So just keep that in mind. If you can't get half of one of the two or both, then automatically it is not connecting the points. Alright, the situation above is an example of what we call a function. We would say that the number of fish caught is a function of the number of hours that Jason spends fishing. So we'll talk a little bit more about functions here in just a moment, but just know that that one is a function. Shawn is also spending the week fishing. However, he is fishing in the Bear River. Each day he records how many hours he spends fishing and how many fish that he caught. The table of values below shows this relationship. So it looks like, how many days did he go fishing, Radical?
5. Ooh, he went for 8 days.
Well, he kind of went 5, but he spent, it looks like, 6 days. 6 days fishing, okay? So each day he records the number of hours he was fishing, and then also the number of fish that he caught. So now that we know what these, let's just get to the graph up in here. And we can see that the x, the number of fish again, the number of fish will depend on the number of hours that he fishes, or usually does. So that's the y is the number of fish, x is the number of hours fished. So we need a scale on at these again. So there can be another 1 hour, then 2 hours, 3 hours, 4, 5 hours. Now I'm doing this every 3 lines just because I have the space to. But you wouldn't have to. The number of fish caught goes up to 8. So looks like we can go up by ones. So 1, 2, 3, 4, 2, 3, 4, 5. There's 5 right to count. 1, 2, 3, 4, 5. There's a 10. And it goes all the way up to 15 again. And we've labeled the axes and have a scale. Next thing we need are the points that good old Shawn found for us. The first one, 1, 4 right here. Then he went 0 and caught 0. Next time he went 2 and caught 5 right here. And then he went 3 and caught 1. And then he went the next day for 3 hours again. But this time he caught 8. And then he went for 5 hours and caught 5. And that's about what you would expect for fishing. Just never really know how many you will catch, no matter how many you fish for. So
He went for fishing for 3 hours one time.
it is not a function. So the number of fishes that Shawn catches is not a function of the number of hours he spends fishing. Well, why is it not a function? That's a good question. So looking at these two, what's the difference between these two graphs? We got Jason on the top, Shawn down below. Yeah?
The first graph thing can actually go in a straight line.
All right, good.
And
So
the second one is scattered.
yeah, this one is in a straight line. This one is scattered. That is actually not what makes it a function. But that's good to remember. We'll talk about linear relationships and how they are related to functions. That is correct.
I just said that.
Oh, sorry, he raised his hand. So, as you can see, he went fishing for 3 hours. And one time he caught 1 fish, and the other time he caught 8 fish, which means we don't know how many fish he's going to catch if he goes for 3 hours.
Exactly, there's a rate of
That is what makes it not a function.
Exactly, I said there's no rate of change.
So it's not a function because we don't know exactly how many fish he will catch if he goes for 3 hours.
There's not a rate.
That is it. So what this means is that it's kind of like a machine. It needs to function like it should. So for example, let's say that you put like a burrito in a microwave, right? And then out comes a donut, right? Well, is that what you would want to come out? No, you put in
Oh
a
yeah.
burrito
Oh, I wanted donuts to come out of the burrito.
and then a donut. Now here's the thing though, is if you put a burrito in again and a donut comes out, then it is functioning. And you know what to expect from this stinking machine, you see what I'm saying? So then it would be a function.
But what if you put spaghetti in the microwave?
A burrito flavored donut sounds great.
What if it was like
Or a
spaghetti platter?
donut flavored burrito. Either way. Alright, compare and contrast relationship for Jason's week spent fishing and Shawn's week spent fishing. Make a conjecture, which is just a sentence, about what kind of relationship makes a function and what kind disqualifies a relation from being a function. So we have to be able to predict exactly how many or how something will, what will happen to something if it happens again. So for example, if he fishes for 3 hours, Shawn, we don't know what could happen. If Jason fishes for 3 hours, it appears that we know what would happen.
Because there's a function.
Because it is functioning. Well, what about number 4? Vanessa is buying gumballs at Vincent's drugstore. The map in below shows the relationship between the number of pennies, or X, she puts into the machine and the number of gumballs she gets out, or Y. Well, we haven't talked about mappings just yet, but this is one of them. Which means, right, X is the number of pennies, right, Cal? So pennies. And the Y is the number of gumballs. So, if he puts in 1 penny, he gets 2 gumballs. 1, 2. And yes, that is an ordered pair.
Wait, why are there
If he puts in 2 pennies, we get 4 gumballs. 3 pennies gives us 6 gumballs.
You draw the line.
And 4 pennies gives us 8 gumballs. Right here. All right.
Have an iPad.
So, does this look like it would be a function?
Yeah.
For example, if you put in 2 pennies, do you know how many gumballs you would get? Yeah, it appears that you would. So this one appears that it will be a function. Let's look at the table though. Alright, so up there we had 1, 2, 3, and 4 pennies. And we got 2, 4, 6, and 8 gumballs for those pennies. Now let us look at the graph. That's very nice of them. They already labeled the graph for you. So we just got to put the points up and count. And right there we got 1 penny gave us 2 gumballs. 2 pennies was 4 gumballs. 3 was 6. 4 was 8. Bam! So, nothing unusual about this one. They didn't put in, for example, 3 pennies and suddenly got 10 gumballs. So that'd be weird. I mean, it'd be good, yeah. But that would show that the machine now is malfunctioning. So, what comes next is we need the equation up in here. And this should be in slope-intercept form, which some of you guys still don't know how to do, even though it was 2 units ago. So, this may be a part that you want to pay very close attention
We
to.
learned it when there was a sub, Mrs. Bagley.
When it was snowing?
Miss Bagley was.
When it was snowing.
No, it wasn't snowy at all. Oh,
Alright, does anyone know what the sloppage is up in here?
it looks like sludge.
It's close.
1 X.
No. No! Just no X. It'd just be 2.
0 X.
I heard 2X.
Oh.
2. Sloppage is 2 because we went up 2 to the right 1. And we went up 2 to the right 1. Constant rate of change, up 2 to the right 1.
Up to
And the y-intercept on it, these,
0.
it is 0.
So it's just
For example, if he or she has 0 pennies, you should get 0 gumballs. Okay.
okay.
Anything else would be, well, stealing, which is bad. So,
We had -1.
just out of curiosity for these, would we connect the points?
Yes. It's working.
And that's just determining if it's a function or not. It is a function, but that doesn't determine if we connect the points or not.
No, because you can't have half gumball.
Bam! The machine is not spitting out half gumballs. Therefore, you either have a gumball or you do not. This one we would cannot. We would cannot. We now beep pop. We would not connect the points
Spitting out half.
because you can't have half a gumball.
What?
You should. Kevin is across town at Marley's drugstore. The mapping below relates the number of pennies he puts into the machine and how many gumballs it gets. So the first arrow right here. All right. For example, this is pennies, and the y is the number of gumballs. So the first time he puts in 1 penny, bam, 2 gumballs. Kevin is a happy person.
And there is a function.
The next time, bam, we get 2 pennies gives us 3 gumballs, so it's not proportional, but that's okay. So he says, you know, I'm going to try 2 pennies again, and bam, now I get 4 gumballs.
So now it must be real.
And then the last one, just to check, Kevin puts in 3 pennies, bam, 6 gumballs. Well, Kevin realized that something unusual is going on with this machine, because if he puts in 2 pennies, he doesn't know how many gumballs are going to come out.
So there's no functioning.
All right, so let's fill out the table. We kind of filled in the values there. 1, 2, 2, and then 3. Then we got 2 gumballs, 3 gumballs, 4 gumballs, and 6 gumballs, respectively. Now, again, this graph is labeled for us, which was extremely generous. All we need to do is put the points on here. 1 penny gave us 2 gumballs. 2 pennies gave us 3 gumballs, and then 2 pennies gave us 4 gumballs, and then 3 pennies gave us 6 gumballs. So, is this one functioning? No, the machine is malfunctioning, specifically with 2 pennies. Alright, Cody is at Ted's drugstore. The graph below relates the number of pennies he puts into the machine on different occasions and how many gumballs he get out. How does this machine work?
When you put in 1,
You get 10.
get arranged from 1 to 10 gumballs.
That is correct. So do we ever know how many is going to come out?
Wait, why are
Nope.
we going to
We
drugstores and getting gumballs?
Because that's another name for like a gas station.
Sure.
Well, like a drugstore doesn't always have to be like a drug dealer.
Well, it's not for drug dealing,
Like, well,
but
it doesn't sell like.
well, someone will deal the drugs. Just it's legal.
Like
cocaine.
Like
This is buying
I don't remember
gumballs
hearing
at
anyone
Walt's
say
drugstore.
cocaine.
Yeah.
Kevin is across town.
All right. So is the number of gumballs? Yes, this one is not a function because we don't know how the machine works. Somehow it's just putting out 1 to 10 gumballs for each penny. So compare and contrast the relationship of the gumball machines at the different drugstores. Well, it appears that 2 of them are not functioning and 1 of them is functioning. There we go. That's good enough. The cost for entry into a local amusement park is $45. You can ride an unlimited number of rides. Complete the graph and the table actually. So let's look at the number of rides. Let's say you go on 0 rides for some reason.
Oh, whoa.
And then maybe you go on 1 ride and then 2. Maybe you go for 5 rides or 40 rides. I don't know. Okay. But in any case, how much money will be spent if you go in and go on 0 rides?
$0.
$45.
$45. Wait a minute.
You shouldn't just say stuff when you're not really paying attention there.
Wait a minute, but
I know, but you weren't paying attention. What if you go on 1 ride? How much will it cost?
45.
$45. What if you go on 2 rides?
45.
5.
45.
40 rides.
45.
$45 still, okay? So as it turns out, this one we can see that the amount spent is going to depend on the number of rides, or it should.
What if you went on 46 rides?
What if you went on 46 rides? How much would it cost?
$45.
$45.
That's
So let's go and label these, starting with 0, 1, 2, 3, 4, 5, all the way up to 10 rides. And this one is going to have to go up by 5s each, so there's a 10, 20, 30, 40, and then a 50. Well, let's go ahead and draw our graph up in here. So if we go on 0 rides, it's $45. Bam, there it is.
That's a thick line.
Thank you. Not only is it thick, but it's incorrect. What do we got to fix?
No line.
Everything.
What do you mean no line? Just erase the line?
You had 1 at the 0.
1 had the 0?
There was one.
Well, we did. We can put that point right there.
You don't connect.
Excellent. Very good. We do not connect the dots because if you go on half a ride, then you probably didn't. Well, yeah, it's possible.
Or you'll fall off and you break all your bones.
What if it's a teacup, Josh?
All right. Is this a function?
No. The little crack where these
Yes.
Yeah.
Yes, because you know how much it's going to cost if you know how many rides are going on.
That is correct.
See, I got it
We
right.
know exactly how much it will cost, no matter how many rides we go on. Therefore, it is a function.
So wait, do we put an arrow on the dot or something?
Well, hold on. Is this no really distracting you guys? I expect this out of 70s. I opened it for you guys because you're in 8th grade. The shades. I had to close it for 70s because they're like, whoa!
It's not even trying.
I know, but people are still looking outside like, what?
Now you're making us
Well, it was.
Is it snowing yet? Did it come back on? I just want to know. Do I need to shut the blinds?
Yeah, I need to go shower.
I think Cliff, you had a remote.
The table below shows the number of hours Owen plays his favorite video game and the number of points he scores. That's on, if this is killing zombies, he's barely got enough to pack up after 1 hour. That's not good. But in any case, if he plays,
He barely got enough to pack up.
yeah, right, with the 5,000 points, you can barely even pack a punch right there.
What?
You can with $5,000.
Wait, does he have like 5,000 money?
Wait,
Or
like,
5,000?
10,000
Punch
back up.
something?
No, you do not.
What do you mean, like punch something?
Never mind.
Like, get famous and playing.
You don't have enough energy to hit it.
There's points like energy,
You
something
can buy jug.
like the pack,
Hey,
the packing.
You could buy Jug with that. Not only Jug, but
Jug?
a couple others, possibly.
We're talking about video games? I'm really confused.
Okay, well, one of you understands.
Oh yeah.
I'll take one out of whatever you guys.
I know.
No, it was not.
I understood.
Anyways, just looking at this, because all it's asking is this a function? Looking at these values. So one time he goes, he plays for 1 hour, he scores some points. Another time, 1 hour, some points, 1 hour, 2 hours and 2. Yeah?
It's not a function.
Why?
Because for 1 hour, you get different amount than you do for the next day for 1 hour.
That is correct.
But it isn't a
If- If Owen is going to play for an hour, we don't know how many points Owen will score. Maybe 5,000, maybe 5,550, or 6,500. We just never know. Therefore, it is not a function. Below is a formal definition of a function. As you read it, compared to the conjecture, the statement that you made about what makes a relationship a function, given two variables, x and y. Y is a function of x if there is a rule that determines only one unique y value for a given x value. Meaning you can't have different x values for the same x. You can't have different y values for the same x value. Yep. Describe it in your own words. I just did. Well, let's go through this first and then we'll talk about it. And then hopefully we won't have to talk about it. So first thing is that right now you guys have seen this y equals mx plus b stuff. Not that everyone remembered it on the test, but hopefully you guys will in the future because this is actually pretty crucial. In any case, that is what we call an equation. Today what we're doing, and well, not all the time, but from now on we'll be moving a little bit away from the equation into functions. Now functions are actually extremely different than equations. Okay, so I'm going to show you guys the difference. So we have that equation y equals mx plus b. I'm going to rewrite it as a function. Okay. What you need to do is know the difference between an equation and a function. Here we go. So let's just show this part. Mx plus a b. All right. So it looks pretty similar. This is where the big difference comes in. All right. Here we go. Bam. There it is.
I knew it.
Now that was pretty different. It's pretty different, okay? So, that's, well, it's very different, okay? Because now instead of y, we have that other stuff. Now here's how this would be said. Just this part right here. That would be said f of x. What that means is this is a function, f stands for function, It's a function of x, meaning that whatever value we get there, which is actually the y value, will depend on whatever the x value is. And yes, I know you guys say that this is common in science, right? Dependent and independent variables. Well, they stole it from math, the jerks. So just know that this is where it originated from. Functions, dependent and independent variables. X is independent. F of x is dependent on x. The f depends on x. So to start off, we got Jason is spending the week fishing at the Springville Fish Hatchery. That seems kind of cheap. It's a hatchery, so they're just right there, aren't they? Each day he catches. That was close. 3 fish for each hour he spends fishing. This relationship can be modeled by the equation y equals 3x. Let's look at this y equals 3x garbage. Y equals 3x. Let's say that we wanted to change this into a function. Well, how would we change this into a function?
Would you just change F?
What?
F3 equals 3x.
It's close. It's close. Well, we do get rid of the y, and we replace it with the f of x. Bam, that is all we would need to do. All right, now that's just a notational thing, by the way. I know you guys are really confused by that right now because I haven't finished explaining and we haven't finished the lesson. If at the end of the lesson you're still confused, that's okay. Ask your questions, okay? Well, let's look. Where x, oh, that's nice. They said what x represents, the number of hours you spent fishing, and y, or f of x, would represent the number of fish caught. So, for example, if he spent 3 hours fishing, how many fish would we expect him to catch?
F of
F
12.
F times F.
3x.
Yeah, 3 times the x, which is the hours fishing, 3 times the 3 hours
3x.
would be 9 fish.
9 times 3 equals 3.
Why would
Let me show you this, okay? So f of x, we want to know if that first one. How many hours did he spend fishing? The first one there? 3 hours. So the function,
Joe's right.
the function of 3 hours would equal, well, we did 3 times 3 already, 9 fishes.
So is the function just how much it goes up?
Now the nice thing about this is we can change this immediately into an ordered pair. X was 3, the y is 9, or f of x. Well, that gives us a point on this graph, which we can now put on the graph. 3, 9, oh, 9's not labeled very well.
Mr. Salbut.
Alright, so to finish off this graph, we need labels. And y represents the number of fish. I like fish. I like fish and rice and seaweed stuff. Sushi.
Yeah, I like sushi.
Sometimes I like just rice and fish, and that's okay too. That's nigiri, right?
No, rice fights.
This is the number of hours. Alright, now that we have that labeled, and I only knew the labels because they told us. But I could have known the labels because I know the number of fish will depend on the number of hours. So number of fish is dependent on the number of hours. Well, that gave me the 0.39er, which would be this point right here. I guess that cleared things up then.
Here, just take the money and give me
So
the
3 represents the 3 in front of the x. The coefficient is the sloppage. 3 fish every hour. So if we multiply that by 3 hours, 9 fish, okay?
That's what I said 5 minutes ago.
Okay!
So much.
Alright, so if you spend 2 hours fishing, how many fish would you catch?
6.
6. If you spend 1 hour fishing, 3 fish. 2 hours,
6.
6. 0 hours,
0.
4 hours, 12. Bam, there you go.
They're just
Alright, well let's go ahead and graph all of it, these. Let's graph them, right? So we got 2, 6. No, they're in order, aren't they? Let's compare this to the second one.
Just take the money and give me the
so
test.
complex to everybody else.
Let me Let me do this other one. This was f of 2.
Kind of, yeah.
I sort of understand. It's basically
I'm pretty sure I understand it.
All right. The function for 2 hours of fishing
But where did the X
would give
go?
you
The X is just
6
all of a
fish.
sudden?
No,
That's amazing.
they replaced the X with 3.
Bam, there it is. Now the question is on this graph, would we connect these points?
Yeah.
Harmon?
Whoever made this equation's on crack.
Nice. Now, would we connect the points?
No.
Yes.
No,
Wait.
because you can't have half a fish. Which would, like, if we connect these points right there, that indicates you'd have, like, a part of a
When you
fish.
got them, you have
Okay.
to get rid of all of it, and then you only have.
So there would
Yeah, right. You get rid of all of it, or you keep all of it. The situation above is what we call a function. Because it was functioning, we could say that the number of fish caught is a function of the number of hours Jason spends fishing, which is why we can use f of x. However, on this one did not give us an equation to change into a function. So we're just going to graph these points and determine if it is a function, kind of. So, for example, let's go ahead and put a scale on this graph first, and then we will label the axes, okay? So right here, we can see it goes up by 1 hour of fishing. It goes up to about 5 hours, and hours is independent right here.
I need to take 3.
And then the number of fish caught will be dependent on the number of hours fished. So fish is y and x is hours, independent. X is independent. And then we need a scale. This goes up, should be number of hours, it goes up to 5 hours. So we can skip, this is 1 hour, 2 hours, 3 hours. Every 3 lines is an hour there. And then number of fish. This goes up to 8 fish right here. So, yeah, looks like we'll have to go by ones right here. 1, 2, 3, 4, 5 fish. 6, 7, 8, 9, 10 fish. And that's about as far as I need to go up in here. Well, this first line shows that he spent 1 hour fishing and caught 4 fish. So let's go ahead and graph that point. 1 hour fishing produced 4 fishes. Well, the next time he goes fishing, he finds that he spent 0 hours fishing and caught exactly 0 fishes. So that gives us this point right at the origin. The next time he goes, old Shawn, he spends 2 hours and catches 5 fishes. So 2 hours, 5 fish, right here. And then the next time, 3 hours, produced 1 fish right here. So 3 and 1, right there. But the next time he went 3 hours fishing, he caught 8 fishes. So that would be up in here, right there. And then finally, the last time, spends 5 hours and catches 5 fish. And that's about what you'd expect with fishing, right? Because sometimes you catch nothing, and you spend 4 hours fishing. Other times you spend 3 hours and catch maybe 1. But you could catch 8 as well. And then you eat them. That is correct. This one, as we can see, yep, it's not a function, and here's a why.
How do you know if it is a function?
Functions are not depending on linearity, and they do not depend on, what was the one you mentioned, Gavin? Continuity or discreteness, like these ones are. All right, so let's look at these two graphs. So what do you guys notice that's different between these two graphs?
One of them is like a straight line.
Yeah, good. Good, so Jason, his is a straight line up here at the top, right? You got a straight line up in here, right there. And then Shawn's, his is kind of all over the place, but there's something else. That's not really, again, linearity does not determine if it's a function or not. There's something very different about Shawn's right here at the bottom. Something unusual.
Fishing for 3 hours.
That's part of it. He did go fishing for 3 hours 2 different times, right?
Oh, he's realistic.
2 different times. But what happened when he went fishing 2 different times for 3 hours? He got 2 different answers, right? What that means is that when Shawn goes fishing, it's malfunctioning. Because if he goes 3 hours, does he know exactly how many fish he's going to catch? No. Because right here he's proven one time he went and caught 1 fish, the other time he went and caught 8 fish. That means that this is malfunctioning. It's malfunctioning, it's unpredictable, therefore this one is not a function. A function allows us to accurately predict what will happen. For example, if Jason went fishing for 5 hours, we should know how many fish he will catch. Or if he goes fishing for 2 hours every time, he should catch 6 fish all the time. But if we just go fishing in the lake, perhaps, like Shawn did, then we may not know exactly how many fish we'll catch for any number of hours we fish. Okay? So that's why it is not a function, because we can't predict how many fish he will catch fishing randomly. See a hatchery, there's just fish right there. Or we could say again that it's like a machine that malfunctions, right? Like if you put a burrito into the microwave and when you open it, you expect a burrito to be there, right? That would be functioning. But if you throw it in there and a donut comes out, what the heck happened there? See what I'm saying right there? Okay. So it's because then it would be malfunctioning. I'm not saying there's anything wrong with that, unless you really wanted a burrito. Unless it was like a donut burrito, a burrito donut. Oh, that sounds pretty good actually. Vanessa's buying gumballs at Vincent's drugstore. Yeah, they used to have drugstores, okay? The mapping below, there's a drugstore in Pleasant Grove. It's called the pharmacy.
Hey, Vincent Drugstore is from...
The mapping below shows, this is a mapping, we haven't gone over mapping. I'll explain what that is. The mapping below shows the relationship between the number of pennies or X she puts into the machine and the number of gumballs she gets out, or wham. Alright. Alright, so what this is saying, what this says right here, is that, so in other words, 1 penny, what the heck, 1 penny produced 2 gumballs.
What?
2 gums.
Oh, I wish that happened.
That's what this represents right here, okay?
What kind of sick world is this?
What, you
That's
want,
not sick, that's great.
yeah, isn't that great? 2 gumballs for 1 penny? You want 1 gumball? Okay, that's fine.
You could literally put in $1 and get 200 gumballs.
What is this? You should get
Think
five
about
for one
it. You put
penny.
in
No, if you think about it though, what if
you
these
get one
gumballs were like
You find in the school hall.
Alright, so the second one, the second one right here, who can explain what that would mean?
That would mean 2 pennies for 4 gums.
2 pennies for 4 gumballs, right? And then it works its way down. By the way, these would be ordered pairs essentially as well. So down here when we look at this table, number of pennies. Up there from the mapping we got 1, 2, 3, and 4. And the number of gumballs produced was 2, 4, 6, and 8. And well, that's nice of them to label the axis for us on the graph. So on this graph, let's go and graph these points. We got 1, 2. I guess it'd be more like right there. 2 and 4, 3 and 6, 4 and 8. So we should be able to write an equation for this. But before we do, would we connect these points?
No, because you can't get half a gumball.
That's correct. The machine should not be spitting out half gumballs. That'd be great, right? Yeah. Oh, that'd be yucky. All right, let's write the equation for these. So we should write this in slope-intercept form. We got y equals mx plus a b. And this, I think, was on the Unit 3 test stuff, which some of you guys still need to pass, so this would be helpful in that scenario. So what is the sloppage on these? Well, we can see, yeah, you can use the triangle stuff or the stair steps. However, Yeah, it goes up to the right one. Now, if you want to write that as 2, that's fine. We don't really need the fraction. Do we know where the y-intercept would be? Certainly, it would be at 0. Because if you put 0 pennies in, how many gumballs should you get out? 0. Okay. So hopefully this equation makes sense. Is this one a function though?
No.
Yes.
No, because it doesn't have the F.
Okay, so now remember, it's not a matter of if we write it as an equation or a function. It's more a matter of can we predict how many gumballs will come out for how many pennies we put in?
Yes.
Yes, we can. Because so far it's showing consistency. The machine is showing consistency. Therefore, the machine is functioning. So this one would be considered a function. Which also means that we could go in here and change this equation, which you guys love, into a function. Bam. Let's change this 2x to make it look a little bit more pretty than it is. By the way, you don't really need the plus 0 either. That's not really important. Alright, this is also an example of a function. So yeah, we know it's a function because they said at the bottom. We would say that the number of gumballs received is a function of the number of pennies put in the machine.
Wait, it's 100 and
Alright, let's look at Kevin. This is number 5. Alright, Kevin is across town at Marley's drugstore this time. And this mapping shows, relates the number of pennies he puts in to the machine and how many gumballs he gets out, okay? Now there's something different about this mapping. So right here, see he put in 1 penny right here. 1 penny and he got how many gumballs? 2 gums. Okay, so he's a pretty happy dude. So the next penny he puts in, that's this arrow. See he puts in 2 pennies, but then he gets 3 gums. Okay, well that's not proportional, which is okay. But then he puts 2 pennies in the next time, and what comes out? 4 gums.
so it's on Xbox.
And this guy has to wonder what the heck is going on with this thing. So he puts in 3 pennies, and what comes out? 6 gums.
Can we just say $3?
Now that's how this mapping works here. Each arrow provides an ordered pair out of these. So let's go ahead and fill out the table. There we go. Number of pennies. We got 1 pennies, 2 pennies, 2 pennies, and then 3. The 1 penny gave us 2 gums. The 2 pennies gave us 3 gums, but then 4 gums, and then suddenly 6 gums for 3 pennies. So let's go ahead and graph all of these points. So 1 penny gave us 2 gums, and then 2 pennies gave us 3 gums, but then 4 gums. Uh-oh. And then 3 pennies, we got 6 gums. Function or no? Oh yeah, it's good to hear. Some of you guys noticed that with just the mapping. Yeah, 2 pennies provided or produced different numbers of gums. So we can't predict how many gums will come out for 2 pennies. Now we could be close, but we don't know for certain how many would come out there. All right. This is an example of a relationship that is a function. Not a function. I didn't see the word not there. All right, Cody is at Ted's drugstore, and this is what he finds in this gumball machine. Very, very, very strange. Well, based on the graph, how many pennies did he put in the first time? Well, we don't know, but how many pennies come out for 1 penny? I'm sorry, how many gumballs come out for 1 penny?
2.
Sometimes 2, sometimes
1 through 10.
3, maybe 10, right?
See, that's the option.
So is that gumball machine functioning?
No.
No, it is not functioning because whenever we put 1 penny in, we don't know how many gumballs are going to come
9
out.
more fell out.
It's like a penny.
Then he
or
made
a dime.
All right, I'm going to do this problem. The cost for our entry into local amusement park is $45. Once inside, you can ride an unlimited number of rides. Complete the graph and table below. So let's look at number of rides. Let's start with 0. Oh, that's kind of big. And then we'll look at one ride and maybe 2, maybe 4, and I don't know, maybe you want to do it 50 times, whatever. But in any case, let's say you ride 0 number of rides, but you just go into the amusement park. How much would you pay?
45.
$45.
So
If you ride 1 ride, how much would it cost? $45. 2? 4?
5.
Yeah, it's just going to be $45. You'll have only paid $45 no matter how many rides you go
But
on.
wouldn't that still be considered a function?
Oh, yeah,
Because you know what
don't
you're
even
gonna do.
Let's find out. Let's find out. So X is the number of rides.
Oh, because it's dependent on the amount I see.
Y is the dollars spent.
Oh.
So the scale, we got 0, 1, 2, 3, 4, 5.
This is a function.
1, 2, 3, 4, 5. Let's go up to 10. Number of dollars, 0. 1, 2. And let's make these go up by 3 each. 3, 3.
Yeah, I get that.
3, 6, 9, 12, 15. 15, 18, 21, 24, 27, 30. There we go. All right, well,
Wait,
I didn't make it to 45, dang it. I got to change my scale. And that's
We
okay.
should do it by 10.
Let's do
Let's go by 5 should work. Thank you. So let's go by 5. So there's 10, 20. That's me right there. 30, 40. Yeah, 50. This one will work. 5 will work. So $45, 0.45 right here, and it'd be all the way over here. What's wrong with this graph, though?
It's straight.
No,
It's function.
It's horizontally straight.
no.
It
doesn't say 0.
It doesn't have a slope.
It doesn't.
It doesn't have a slope, and it has.
It's still
And the
function.
y-intercept is 40.
It's a
No, no, no. That y-intercept's good. It's 45, right? 0.45.
No.
But it's
Labeled?
still a function, right?
Oh.
No answer.
It is a function, but
Alright.
if we look at this, can you go on half a ride?
That's
No.
facts.
So as it turns out, this one would be discrete.
Well, you can just jump.
So be
off
very
it,
careful.
or it just closes down.
You still went on a ride, though. So it'd be all these points, right?
Yeah.
But like, why is it like ride 0 rides for $45? Like, oh yeah.
Because you got to pay money to go into the park. Bam.
Just sit-
So the graph should look like these. You can't connect the points because you can't go on half a ride. So is the amount of one spends a function? Yes, it is. Because no, if you go on 10 rides, you would know what you would pay. They're not going to charge you differently, different times.
It was like, never mind.
The table below shows the number of hours Owen plays his favorite video game and the number of points he scores. Function or no?
I was just wondering if I remember.
All right, function or no on these?
No,
It is not a function. Why?
because he could spin the box with the ray gun first, or
You didn't get the ray gun first?
Of the triangle.
I hate the ray gun, man. It's got that backfire stuff that
Inefficient.
they kill you if they get too close. You know what I mean? But anyways, yeah, that's pretty much true. See, he played 1 hour and he got 5,000 points. But here he played another 1 hour and got a different number of points. So that's inconsistent. We don't know how many points he would score in 1 hour, even though we can kind of predict about how many. It's not the same. It needs to be exactly the same every time. And it happened again for 2 hours. One time he played for 2 hours and got 11,300. Another time he played for 2 hours and got 12,400. That's different. So we can't know exactly how many points he would score based on the number of hours he plays the video game. But if he can only play for 3 hours, then he probably isn't very good at killing zombies. So.
Triangle is the hypothesis.
Bro, he has enough to pack a punch.
He
No, no, he doesn't. It's
He does.
5,000.
For 3 hours, he does.
Undermine's 5,000.
He could pack 3 times.
Yeah, there you go.
He could actually pack twice and then,
Get judged.
upgraded. He could get Juggernaut. I got you.
Speed.
All right, anyways. Below this is a formal definition. Given 2 variables, let me start that over. Given 2 variables, that sounds better. X and y. Y is a function of x if there is a rule that determines one unique y value for a given x value. So again, if whatever x is can only put out one number, not 2 different numbers. Okay. Describe in your own words what a function is. It's like a machine that functions.
Well, already did that for fun.